Let's talk about cardinality. Cardinality is the measure of a number of elements of a set. In the database world, a set is an entity. But take a look at this. Set A is composed of those elements. So what is the cardinality of set A? Well, it's 5 because there are 5 elements inside set A, and it doesn't matter what those elements are. It could be numbers, letters, objects. It could be 1, 3, t-shirt, 7, 9. The cardinality of set A is 5 because there are 5 elements in the set. Remember that we can compare two sets as a relationship, and of course certain types of relationships are functions, as we saw in the last lecture. Look at these two sets, y and x squared. They don't have names, but in the previous lecture we called them set A and set B, and we said that the relationship between them was squared. So we say the cardinality of set y is 5 because there are 5 elements. The cardinality of set x squared is 5 because there are 5 elements. And we can also say that set y equals set x squared because they have the same number of elements. There are 3 types of functions I want to talk about. And again, this is just some more of that mathematical groundwork for database theory. So we have an injective function. Every member of set A has its own unique matching member in set B, and I'll illustrate these in just a moment. We also have a surjective function, where every member of set B has at least one matching member in set A. And finally, we have a bijective function, which is injective plus surjective, and we'll see that that's a true one-to-one relationship. So here's an injective function. Every member of A has its own unique matching member in B. Every member in B does not have to have a matching A, however, so that there's one straggling B there. This is still an injective function. Here's a surjective function. Every element in set B has at least one matching element in set A and can have more than one. So we see that second element in set B has 2 matching elements in set A. And in a surjective function, no member of set B can be left out. And here's a bijective function. Isn't it beautiful? A perfect one-to-one correspondence. Every A has a B and every B has an A. So what does this have to do with databases? Well, take a look at this business requirement statement. Every student has exactly one teacher, and teachers can have many students, but must have at least one. So from that business requirement statement, we can derive that we have 2 entities here, student and teacher, and every student has exactly one teacher. Teachers can have many students, but must have at least one. So every student there is related to one teacher, and every teacher has at least one student, but can have more than one, as we see with student 3 and student 4 having the same teacher. This is an example of a surjective function between 2 entities in a database. When we're determining the nature of the relationship between and among entities in a database, we have to ask 3 important questions. The first question relates to degree. How many entities are participating? And then we ask about the specifics of the participation. What is the minimum number of relationships in which an entity can participate? And the cardinality ratio. And that means what is the maximum number of relationships in which an entity can participate? So let's bring up our student and our teacher again. And we'll ask these 3 questions. What is the degree? How many entities or sets are participating? That answer is easy. 2, student and teacher. The next question is participation. What is the minimum number of relationships in which an entity can participate? Remember our business requirement statement. Every student has exactly one teacher. Teachers can have many students, but must have at least one. So the minimum participation for student is 1. Otherwise, according to the business requirements, if they don't participate, if they don't have a teacher, then they can't be a student. And likewise, teachers can have many students, but must have at least 1. That's the minimum for teachers, so 1 for teacher as well. Now we look at the cardinality ratio. What is the maximum number on each side? Well, every student has exactly one teacher, so the maximum is also 1 for student. Teachers can have many students, but must have at least one. So the maximum for teacher is going to be many. Let's do this again. We have student and teacher. We're designing a database. We've determined that student and teacher are related. And we ask the questions. Degree. How many entities are participating? 2. Participation of student? 1. Participation of teacher? 1. This is the minimum, remember. Now we indicate that notation on its opposite side. So the participation of student goes over on the teacher side, and the participation of teacher goes over on the student side. Now we move to cardinality. Cardinality of student is 1. Cardinality of teacher is many. Remember, these are the maximums. And we do the same thing. The cardinality goes closest to the entity itself. So now we have given a teacher, they must have a student, that's the 1, and they can have many students. And we have given a student, they have exactly 1 teacher, 1 minimum and 1 maximum. We define this relationship, this whole relationship, as 1 to many or many to 1. And to define any relationship, we look at the cardinality on both sides. We look at the maximums on both sides. So this is a 1 to many or a many to 1. It doesn't matter in that regard. So let's talk about the specific symbols we use in this class to indicate participation and cardinality. And we're going to use crow's foot notation. It's also known as Barker's notation or IE, and it's the notation that I see most often out in the professional world. There are other popular notations too, like Chen's or IDEF1X, but this notation works very well, and it's a notation that I see, again, in the real world very often, so we're going to use it in this class. Here are the symbols for crow's foot. We have an open circle for optional, a vertical line for mandatory or for a cardinality of 1, depending on where it's placed. And we have that little crow's foot symbol for cardinality of many. Let's look back at our student-teacher relationship. And we have participation on each side of 1, which also means mandatory participation, right? A student must have a teacher and a teacher must have a student. So we're simply going to draw a vertical line on the opposite side. And now we have cardinality of student 1 and cardinality of teacher many. We're saying given a single teacher, they can have many students, and given a single student, they have exactly 1 teacher. So we put the cardinality symbol close to the entity and on the opposite side. And what kind of a relationship is this again? It's a many to 1 or a 1 to many. Let's try another one. Every customer has exactly 1 account. Accounts are assigned to exactly 1 customer. So we have 2 entities here. So the degree is 2. Let's ask participation. Participation of customer. So we say given a single customer, must they have an account? The business requirements state that every customer has exactly 1 account. So yes, a customer must have an account. Now let's ask participation of account. Given an account, must it be associated with a customer? And according to the business requirements, yes, accounts are assigned to exactly 1 customer. Now we ask the cardinality question. Given a single customer, can the customer have more than 1 account? Again, going back to the business requirements, every customer has exactly 1 account, so no. The maximum is also going to be a 1. And now let's look at the cardinality of account. Given a single account, can it be assigned to more than 1 customer? And according to the business requirements, no, exactly 1 customer as well. So we have a true 1-to-1 relationship here. Let's take a look at another one. Suppliers can supply many parts. Parts can be supplied by many suppliers. Interesting. So, degree is 2. And let's take a look at participation of supplier. We say given a single supplier, does it have to supply a part? Must it supply a part? And the answer is no, actually. The participation is optional. And same with part. Given a single part, must it have a supplier? According to the business requirements, that's optional as well. It just says they can supply many, but it does not say they have to supply 1. Now let's take a look at cardinality. Cardinality of supplier. Given a single supplier, can that supplier supply many parts? Yes, obviously, according to the business requirements, suppliers can supply many parts. From the other side now, given a single part, can it come from many suppliers? And the answer is yes. So now what we have is a many-to-many relationship. And please remember, this is a conceptual many-to-many relationship. In an actual database, we would not want to do it this way. Let me show you why. Let's say that many students can have many teachers. There's a relationship, there's some more relationships. It creates a huge mess to have a many-to-many relationship. It is a resource drain on the database, and it is considered poor design. So as designers, what we need to do is create a new entity that goes in the middle called an associative entity. Now, instead of a many-to-many, we have two relationships that are one-to-many, with the many side being an associative entity. And the associative entity is simply named a combination of the two entities it associates with, so supplier part in this case. And the attributes of the associative entity are simply the primary keys of supplier and the primary key of part. And now we can make that look quite a bit cleaner. Thank you for joining me on this discussion about cardinalities. I look forward to seeing you next time.